All right, welcome back. So we use the internet all day, every day, right? But have you ever really stopped to think about what's going on behind the screen? It seriously feels like magic. You click a link and bam, a whole world of information just appears. But it's not magic. Not at all. It's some seriously clever engineering. So today, let's pull back the curtain and demystify that incredible journey your data takes every single time you go online.
So yeah, that's the big question we're tackling. How does one simple click, just one little request for a web page or a video, how does it manage to find its way through this global maze of wires and waves, get to a server maybe thousands of miles away, and then come all the way back to your screen in like the blink of an eye? It's wild. Let's trace that exact path, starting right from the ground up.
Okay, so before we even get into all the fancy software and rules, we've got to talk about the physical stuff, the actual tangible things that are the bedrock of any network. We're talking about the hardware, the real roads and highways our data has to travel on.
And there's a technical term for these roads, transmission media. All it really means is the physical path that carries information from point A to point B. The best way to think about it, if your data is a car, the transmission media is the pavement it's driving on. And just like real roads, they come in two very different flavors.
So those two types are what we call guided and unguided media. Guided media is exactly what it sounds like. It provides a physical, contained path. Think of it like a tunnel or a pipe. Basically, it's a cable. Then you have unguided media. That's all your wireless stuff. It sends signals right through open air, kind of like a radio broadcast. Let's dig into some examples of each.
All right, for guided media, you're going to recognize these. First up, twisted pair cable. That's just the standard copper wiring you find in your everyday Ethernet cable. Then there's coaxial cable. That's the thicker, insulated one that probably brings cable TV into your house. And then you've got the superstar of the group, fiber optic cable. This stuff is amazing. It uses pulses of light zipping through tiny strands of glass to send data at absolutely insane speeds. It's pretty much the backbone of the entire modern internet.
Now, on the unguided, or wireless side, we're talking about different kinds of waves. You've got radio waves, which are omnidirectional. That just means they spread out in all directions, which is perfect for things like your car radio. Then you've got microwaves, which are the opposite. They're unidirectional. They travel on a straight line. That's why they're so good for things like cell phone towers that need to be aimed at each other. And finally, you've got infrared. That's for super short-range stuff like your TV remote control.
Okay, so we've got our building materials now, all the cables and the waves. But how do we actually arrange them? You can't just randomly connect a bunch of devices and hope it all works out. You need a plan, a blueprint. So let's look at how these pieces are actually put together to build the structure of a network.
And that blueprint has a name. It's called a network topology. Really, it's just the layout, the way all the different devices on a network are physically arranged and connected. And the shape of that layout, it has huge implications for everything: cost, speed, and especially reliability. The topology is what decides how well a network holds up when something inevitably goes wrong. First up is the star topology, and I can almost guarantee you have one of these in your home. Your Wi-Fi router, that's the central hub, and all your devices, your laptop, your phone, your TV, they all connect directly to it. The big advantage here is that it's pretty robust. If your laptop's Wi-Fi flicks out, your phone is totally unaffected. But, and this is a big but, what's the major drawback? If that central router goes down, yep, the entire network is gone. Next, we have the bus topology. So picture one long cable, kind of like a backbone, and all the different computers and devices just tap right into it. This was actually really popular back in the day for office networks because it was super simple and cheap to set up. But it has one massive critical weakness. If there's a break anywhere in that main cable, the entire network goes down. Way too fragile for most things we do today.
Then there's the ring topology. And just like the name says, each device is connected to two others, forming a literal circle. Data usually travels around the ring in just one direction, getting passed from one device to the next. But just like the bus topology, it's got a major point of failure. If any single link or device in that ring breaks, the whole circle is broken, and all communication just stops.
And finally, we get to the mesh topology. This is the king of reliability, no question. In a full mesh network, every single device has a direct, dedicated connection to every other device. What this does is create a ton of redundant paths, so it's incredibly robust. If one connection fails, data just takes another route. It's awesome for security and for avoiding traffic jams, but, as you can imagine, it's insanely expensive and complicated to set up.
This is exactly why this kind of design is used for the core internet backbone, the places where failure is just not an option.
So this table really sums it all up nicely. As you can see, there's no single best way to build a network. The star is a great, balanced choice for homes or small offices. The bus is cheap, but super fragile. The ring is simple, but it also has that single point of failure. It's always a balancing act between cost, how easy it is to install, and just how important it is for that network to stay up and running.
Okay, so we've got our physical roads and our network city plan, our topology, but for all the data traffic to actually flow without crashing, everyone needs to follow the same rules of the road. And this is where we shift gears. We're moving from the physical world into the abstract world of software and rules.
Think about it. For two devices to understand each other, especially if they're made by different companies in different parts of the world, they have to speak the same language. In networking, we call that shared language a protocol. Protocols are just the agreed-upon rules for how data is supposed to be formatted, sent, and received.
But here's the thing. One single protocol can't do everything. It would be way too complicated. So, networking tasks are broken down into a series of layers. We call this a protocol stack. The best analogy is a set of building blocks, or maybe even an assembly line. Each layer has one very specific job. It does its job and then passes the work on to the next layer in the line.
Now, the most famous theoretical framework for this is called the OSI model. It breaks everything down into 7 distinct layers. Don't worry, you don't need to memorize them all, but the idea is key. The top few layers are all about your apps and your data. The middle layers handle making sure the message gets there reliably and finding the right path. And the bottom layers? They do the dirty work of actually turning your data into raw bits, those electrical signals or pulses of light, and shoving them onto the physical cable.
So the OSI model is a fantastic way to understand networking, but the model that actually runs the internet today is called TCP/IP. It's way more practical, a condensed 4-layer version. It basically squishes some of the OSI layers together, but keeps the really important middle layers, transport and internet, separate. This is the one that's actually doing the work out there.
So what's the real difference here? The easiest way to think about it is this. The OSI model is the perfect, detailed architectural blueprint for a skyscraper. It's the theory. TCP/IP, on the other hand, is the actual skyscraper that got built. It's the real-world implementation that won out and became the standard for the entire internet.
All right, we've talked about the physical wires, the network blueprints, and the rules of the road. So now, let's put it all together. Let's follow one tiny piece of data on its epic journey from your screen all the way out into the world and back.
So it all starts with you. You're in your browser, the application layer, and you click a link. That request gets handed down to the transport layer, which chops it up into nice, neat little packages. Then the network layer slaps a destination IP address on it, just like putting an address on an envelope. It keeps traveling down the stack until it hits the very bottom, the physical layer, where your click is literally transformed into electrical signals or pulses of light and shot out onto a cable.
And really, that's the key takeaway from all of this. From the very real physical cables running under the oceans to the abstract rules and protocols managing the flow of information, the internet is just a masterpiece of layered design. Each layer solves one specific piece of the puzzle, and that's what allows this unbelievably complex global system to work so seamlessly.
I mean, think about it. This is a system that has scaled up from just a handful of computers to billions and billions of devices. It's just incredible. And it really makes you wonder, as our world gets even more connected with things like the Internet of Things and AI, are we going to need brand new layers to manage all that new complexity? What do you think the next layer of the internet will be? Something to think about. Thanks so much for joining me.